Welcome to The Explainer. Today, we're diving into the essential, and honestly kind of beautiful art of purification in organic chemistry. We're going to break down the blueprint chemists use to get from a messy, complicated mixture to a single, pure substance.
You see, in chemistry, making a new compound is really only half the story. The other half, and you could argue it's even more critical, is cleaning up the mess you inevitably make. You start with the problem on the left, this murky, impure gunk, and your whole goal is to arrive at the proof on the right, beautiful, pure compounds.
And this is just a fundamental truth of the field. It doesn't matter if you're pulling a compound from a plant or making it from scratch in a lab, you almost never, ever get a perfectly pure product right away. So every chemist has to have a solid strategy to isolate exactly what they need from all the other junk.
So, how do you actually know when you've succeeded? Well, you have to prove it. Purity isn't something you can just assume. It's something you have to physically measure. A truly pure organic compound has a very specific, razor-sharp melting or boiling point. But impurities? They mess everything up, causing the substance to melt or boil over a wide, messy range of temperatures.
Okay, so how do we actually fight back against these impurities and get to that nice, sharp melting point? Well, it's time to open up the chemist's toolkit and see what we've got.
Now, the most important thing about this toolkit is that you don't just pick a tool at random. It's always a strategic decision, and it's based on the fundamental physical differences between the thing you want and the contaminants you're trying to get rid of.
First up, we've got a really clever trick called sublimation. This technique is perfect for a special class of solids that, when you heat them, turn directly into a vapor. They completely skip the whole liquid phase.
So here's how it works. You gently heat up your impure solid mixture. The compound you want, poof, it vaporizes and floats away as a gas. Meanwhile, all the impurities that can't do that, they just get left behind as a solid. Then you just cool that gas down somewhere else, and it re-solidifies, now in its pure form. Pretty neat, right?
Next up is a real workhorse for purifying solids: crystallization. This whole technique hinges on one key property. Your target compound dissolves really well in a specific solvent when it's hot, but not so well when it's cold.
And the process is this simple, elegant cycle. Step 1. You dissolve your impure solid in just enough hot solvent to get everything into solution. Step 2. You just let it cool down, nice and slow. As that temperature drops, your desired compound can't stay dissolved anymore, and it starts to form these beautiful, pure crystals. But the impurities? They tend to stay dissolved in the cold liquid. So step 3, you just filter the whole thing, collecting your pure crystals and leaving the gunk behind.
Okay, so that takes care of solids. But what if your mixture is all liquids? Well, for that, we turn to the incredibly powerful and versatile technique of distillation.
The most basic version is simple distillation. It's the perfect tool for separating a liquid that boils easily, a volatile liquid, from something that doesn't, like getting pure water from salt water, or for separating two liquids that have very different boiling points. You just heat the flask, the liquid with the lower boiling point turns into vapor, that vapor travels over into a condenser, where it gets cooled down, turns back into a pure liquid, and drips right into your collection flask.
But that immediately brings up a crucial question, doesn't it? Simple distillation works great when one liquid boils way earlier than the other. So, what in the world do you do when the liquids in your mixture have boiling points that are super, super close together?
And this graph shows you exactly why that's a problem. On the left, you've got a big gap between boiling points, so the liquids vaporize at totally different times. But on the right, with that narrow difference, both liquids start turning into vapor at pretty much the same temperature. If you tried simple distillation here, you'd just get a mixed vapor, which would give you a mixed liquid. You wouldn't have separated anything.
So, the solution is to upgrade to fractional distillation. You add this special piece of glassware called a fractionating column. What this column does is provide a huge amount of surface area, basically forcing the vapor through a whole series of mini distillations. With each little cycle of vaporizing and condensing as it works its way up the column, the vapor gets more and more enriched with the liquid that has the lower boiling point. Okay, now for another special case. What if a liquid is so delicate that it actually decomposes, it breaks apart, if you heat it up to its normal boiling point? For that, we use reduced pressure distillation. See, a liquid boils when its internal vapor pressure equals the air pressure pushing down on it. So, by hooking the whole system up to a vacuum pump, we can actually lower that external pressure. And that means the liquid can boil at a much lower, much safer temperature, saving it from being destroyed.
And finally, there's a really specialized technique called steam distillation. This is for compounds that don't mix with water but are volatile with steam. The key to the whole thing is this relationship right here. The total pressure is shared between the vapor pressure of your organic compound and the vapor pressure of the water.
So here's the magic of it. Because the steam is contributing its own vapor pressure, it's doing some of the work. Your organic compound doesn't have to get nearly as hot to start boiling. This means the whole mixture will boil at a temperature below 100 degrees Celsius, which, again, is perfect for protecting a heat-sensitive compound from breaking down.
This matrix just wraps up the whole distillation family for us. You got a big boiling point gap? Use simple distillation. A narrow gap? You've got to use fractional. Have a heat-sensitive compound? You turn to reduced pressure. And for one of those special steam-volatile compounds, steam distillation is your answer. So, with all of these different tools for solids and liquids, how does a chemist actually figure out which one to pull out of the toolkit for a specific job?
Well, they follow a logical roadmap, which is basically a decision tree, just like this one. And it all starts with one super simple question. Is the compound I'm trying to purify a solid or a liquid? From there, it's just a series of questions that guides you to the right technique.
Let's just follow a couple of these paths to see how it works. Okay, say you have a solid. First question, does it sublime when you heat it? If the answer is yes, boom, your choice is made, sublimation. Or what if you have a liquid mixed with other liquids? You ask about their boiling points. Is the gap between them narrow? Yep. Well then, your only option is fractional distillation. It's all just a systematic process of elimination.
You know, when you take a step back and look at all of these methods together, you start to realize they all just boil down to mastering three core physical principles. You're either exploiting how a substance changes phase, manipulating pressure to change when it boils, or you're leveraging its solubility.
And that brings us back to this really crucial point. A chemist doesn't create purity out of nothing. They're more like a highly sophisticated sorter, cleverly using the fundamental laws of physics to isolate the pure stuff from the impure stuff.
And this kind of leaves us with a final thought, doesn't it? If in the incredibly precise world of chemistry, purity isn't something you create, but something you have to painstakingly isolate, what does that say about all the pure things we see around us every day? How many of them are actually truly pure, and how many are just mixtures that have been separated incredibly well?